Welcome to our explainer. Today, we're going to tackle a really interesting challenge in research. What happens when your data points aren't just random strangers? What if they're connected, with a shared history? Let's dive in. It all really kicks off with this one big question. How do we actually measure change? I mean, think about it. Whether we're talking about a patient's health, how a student is learning, or the impact of a new policy, just looking at a single moment in time, it's just not enough. We need to see the whole story as it unfolds. Here's a way to think about it. You could take a snapshot of a forest, right? Just one photo that captures all the trees at that exact instant. And yeah, that's useful, but it doesn't tell you how any of them got to be that way. Or you could focus on the story. Imagine a time-lapse video of just one sapling, watching it grow season after season into a huge tree. See, to really understand growth, you have to follow the story. So, how in the world do we analyze that story? Well, first, we've got to understand the nature of the data itself. We're dealing with information where every single data point has a past, a shared history with all the ones that came before it. This is what we call longitudinal data. And it's pretty much what it sounds like. It's information we gather from the exact same subjects, the same people, the same companies, or, the same trees, over and over again across time. Every single measurement is just another frame in that time-lapse video we were talking about. Now, here's the catch. This is what makes it so tricky. The measurements from our one tree, they aren't independent. They're related. I mean, a tree that's 10 feet tall this year is probably going to be a little taller next year, right? It's not going to suddenly be 2 feet tall. Its height today is directly connected to its height last year. They share a story. And that completely messes with a core assumption of a lot of basic statistical models. That's why I love this way of thinking about it. These data points are basically part of a family. All the measurements from one person or one tree are like siblings. They're way more similar to each other than they are to measurements from a completely different family. And if you ignore that family connection, you're going to miss the real story completely. So how do we handle this? Well, analysts have a special toolkit with methods designed for this exact problem. So let's pull out the first tool, which is all about charting the growth of each and every individual tree. The whole job of this first tool is to respect and really understand the unique path of each individual. Because let's face it, not all trees grow at the same speed. Some might have a sudden growth spurt, others might just be slow and steady. This tool is what helps us model that unique journey. And this tool is called a mixed effects model. The name itself is actually a huge clue. It's mixed because it does two things at the same time. It looks at the big picture trend for the whole forest, but it also zooms right in on the unique individual growth patterns of each tree. It lets you see both the forest and the trees. So here's the bottom line. You reach for a mixed effects model when you want to predict the unique path of one single subject. Your goal is to answer, how is this specific tree going to grow? Or how is this particular patient going to respond? Okay, but what if you're not really interested in one specific tree? What if your question is much bigger? What if it's about the entire forest? Well, for that, we need a totally different tool from our kit. The second tool in our analyst kit is designed for a very different kind of question. Its job isn't to chart one tree's wobbly path to the sky, but to describe the average, smoothed-out trend for the whole group, for the entire population. This method is called generalized estimating equations, or just GEE for short. And GEE is fantastic when you want to know the population averaged effect. It asks questions like, if we used this fertilizer, how would it affect tree growth on average across the whole forest? It zooms out to see the overall effect, not all the individual ups and downs. So there it is, the perfect contrast. While mixed effects models are for predicting the journey of a single tree, GEE is all about describing the average growth of the entire forest. They're two different tools for two very different but equally important kinds of questions. And this right here illustrates the difference perfectly. Let's take medicine. A doctor might use a mixed effects model to ask, how will this new drug affect this one patient's progress over the next 6 months? But a public health official, they'd use GEE to ask, how does this drug affect patients on average across the country? One is subject-specific, the other is population averaged. Okay, now let's add one more layer of reality to this, because data is often even more complex, right? It's not just individual trees. It's trees that are grouped together in forests, and those forests might be grouped together in larger geographic regions. We've got forests within forests. For this kind of thing, we use what are called hierarchical or multi-level models. These are built specifically for data that's structured in these nested levels. Like students nested inside classrooms, which are nested inside schools. You can't just throw everyone into one big pot. You've got to respect that structure.
A multi-level model just breaks the whole problem down into layers. So first, it'll account for the individual tree's growth over time. Then it accounts for things that are shared in the specific forest it's in, like the soil quality. And it could even go up another level and account for the bigger region that forest is in, like the overall climate. It's analyzing the data at every single level of its hierarchy.
So, we've looked at the problem and we've looked at the tools. But why does any of this actually matter? Let's connect these pretty abstract statistical ideas to the real-world discoveries they actually make possible. Because, this isn't really just about trees. These methods are how we track the progression of a disease in a patient over many years. They're how we prove a new drug is actually effective and safe. This is how we understand child development and learning, and how we create public health policies that actually work, all by looking at these long-term trends. In fact, to put a number on it, something like 90% of the studies that determine if a new drug works rely on these exact kinds of longitudinal models. They are absolutely critical to modern medicine in so many other fields. So, when it comes down to it, by learning to read the story inside our data, by respecting its shared history and its nested structure, we can unlock some incredible insights. And that kind of leaves us with one final, really fascinating question. What other hidden stories of change and growth are just waiting to be told in the data that's all around us? And that's our look at longitudinal data. If you found this helpful, you know what to do. Like, comment, and subscribe for more. And definitely let us know in the comments what topics you want us to dig into next. Thanks so much for joining.